Okay, this is the last video about circuits. We're going to be looking at simple circuits that have a capacitor in them. The simplest one is a series RC circuit. So imagine that we have a battery, assumed to be ideal, a resistor, R, and a capacitor, C. Now the other thing we're going to assume is that there's a switch in it. And this switch can switch the battery in and out the circuit. When the switch is in position A, the circuit is said to be charging. If the circuit is in B, it's discharging. We're going to look at the charging circuit first, mostly because the math is a little bit thornier there, and so when we get to the discharging circuit, it'll be easier. But also because that's how you get the charged circuit that you then discharge in B. Now we're going to assume a couple things. We're going to assume that initially the capacitor is uncharged. And we're going to use Kirchhoff's loop rule. We've got a nice single loop circuit here. So let's look at what happens if we go around the circuit like this, starting here. We have the battery EMF, which is positive because we're going from negative to positive of the battery. Any current there is in the circuit is going to be going that way. So since we're going the same direction as the current through the resistor voltage is negative, and as we go across the capacitor, as it charges, the top plate will be positive, bottom plate will be negative, and since we're going from positive to negative across the capacitor, its voltage will be negative as well. And the voltage across the capacitor is the charge on the capacitor divided by the capacitance. Now we're back to our starting point, so that all equals 0. And that's our basic equation for RC circuits. Not too terribly difficult. Now initially the capacitor is uncharged, so what we're looking for is Q as a function of time, but Q as a function of 0 will be 0, and after a long time the capacitor will be charged. So Q of t approaching infinity will be its maximum value, and because it's no longer increasing, the current will be 0, whereas at time equals 0, the current will be at a maximum. If we graph current versus time, it'll look like that, and if we graph charge versus time, it'll look like that, approaching an asymptotic value. That's just based on the qualitative. We're actually going to solve the equation and get Q as a function of time on the next slide, like right now. I'm going to write down that equation again that we're using, which is EMF minus IR minus Q over C equals 0. The first thing we'll do is we'll notice that I, the current, is equal to the rate of change of the charge, so it's dq dt. And we'll rearrange this a little bit so that after a little bit of algebra, we get R times dq dt equals the EMF minus Q over C. And actually, it will be easier if we also multiply the entire equation by C, so that we get C times R times dq dt equals C times the EMF minus Q. And this is what we call a separable equation. We're going to get all the Q's on one side of the equation, all the T's on the other side, then we'll integrate. So you can do this with calculus 2 stuff. And what that's going to look like is that we'll have, on one side of the equation, dq divided by the quantity C times the EMF minus Q equals dt over RC on the other side. And then we'll integrate both sides. Now the integral on the left is easy, or on the right is easy. The integral on the left really isn't too bad, because what we'll do is a U substitution, where U equals C times EMF minus Q, and dq du is just equal to 1. So the integral on the left becomes the integral of du over u. The integral on the right is quite easy. It's just t divided by rc. And then we have to have a constant. C is already taken. It's the capacitance. So I'm just going to, as my constant of integration, I'm going to use d. And now we will bring this whole thing back up to the top here. The integral of du over u is the natural log of u, and that equals t over rc plus d. And substitute c times e minus q equals t over rc plus d. We want to get rid of that natural log because we want q as a function of time. And so we have c EMF minus q equals, oh, hold on. I made a little bit of a mistake. dq du equals -1. So we end up with a negative sign on this. And we can bring that negative sign up here. So CE minus Q equals e to the negative t over RC minus d. And we get Q as a function of time is equal to C times EMF minus e to the negative t over RC minus d. The next thing we can do is say that e to the minus d equals a. We'll define a new constant a that's defined in that way. So this becomes that equation. And now what we need to do is apply the initial condition. At time equals 0, Q is equal to 0 as well. So 0 equals C times E minus A, and now this is e to the 0 power. E to the 0 is 1. This tells us that A is equal to C times E, and as an end result, Q as a function of time is equal to capacitance times EMF times the quantity 1 minus e to the negative t over RC. That is our result. If you would like a 5 on the exam, you need to know how to be able to solve those equations. It's actually not too terribly difficult, and you really only need to be able to solve that one differential equation. You don't need to solve any others. Next, though, we're going to look at something all of you need to know, regardless of what kind of score you want to get, and that is what this means. Now, if we graph that solution, I'm going to write it down here. What we get is Q starts off at 0, and it approaches a maximum value. You can tell that that graph is going to have an asymptote, and that I'll call that Q max, which equals the capacitance times the EMF of the battery. Q equals CV. The question is, what is the significance of that negative T over RC? RC is called the time constant, which is denoted by the Greek letter lowercase tau, and it's equal to the product of the resistance and the capacitance. What that indicates, it has units of time, so this is, and what it tells you is how fast it charges. A large time constant will take a long time to charge. A small time constant will take a small time to charge. I'm going to let you figure out why this is, but the time constant is the time for the capacitor to reach, I believe it's 68% of its maximum charge. So on the graph, the time constant, if this is 68% Q max, the time constant would be right there. Twice the time constant, and I believe it reaches like 95% of its maximum charge. I think 3 time constants is enough for like 98%, something like that. You can calculate it out for yourself. There's a couple of the problems in the back that have you do that. But now, we're going to look at discharging the REC circuit. So now we switch that, we've still got our basic circuit here. See, at this point, the circuit is charged, the capacitor is charged. So there's a positive charge on it. And now we're going to flip the switch to B. When we do that, we've effectively removed the battery from the circuit, and the current will now flow in that direction. If we rewrite Kirchhoff's laws, we'll start here, and we'll go across the capacitor. And notice now we're going from the negative terminal to the negative side to the positive side of the capacitor. So the capacitor voltage, Q over C, is positive. We're still going through the resistor in the same direction as the current. So minus IR. But there's no battery, and so we get back to our starting point, it equals 0. This is actually a somewhat easier equation to solve. It's very similar, but you don't need to do the U substitution. And so I'm going to let you do this on your own, and we'll talk about it a bit in class. But you should find that the solution in this case is charge as a function of time is equal to that initial charge, so the Q max, times e to the negative t over tau, where tau is defined in the same way as it was before. If we plot charge as a function of time, we'll find that it is a falling exponential. It starts off at Q max, and the time constant is once again the time it takes to fall to, I think, 32%, so to fall by 68%. For tomorrow, you should look, I will check questions 10 and 11. Also, please have a go at getting a solution to this differential equation. We'll talk about it in class. For those of you in Calc 2, you should be able to do this. I think small differential equations like this do sometimes show up on the Calc test as well. And that marks all of circuits. Our next topic is going to be magnetism.